Okay, so now we're going to be taking a look at Exam 2, Spring 2018, Question 3. So the question says we want to be able to determine whether or not the series is going to converge or diverge. We want to be able to show all the work and show the test that we're doing. So here we've got the sum from n equals 2 to infinity of n over ln of n, all raised to the nth power. When it's raised to the nth power, I'm going to think of the root test. So I'm going to write that down, root test. Okay, now the root test says I'm going to take the limit as n goes to infinity of my nth root of the absolute value of the thing that my series here, natural log of n raised to the nth power, and I want that to be less than 1 in order for it to converge. So I'm going to put a question mark there because I don't know yet. Okay, so what's going to happen is I'm going to write the limit as n goes to infinity, right? This n, root n, it's like n to the 1 over nth power. Now when I take the nth root of something raised to the nth power, I just get whatever that thing is, so it's natural log. So we're left with the limit as n goes to infinity of n to the 1 over n, all over the natural log of n. Okay, so when I'm looking at this, right, I think, okay, now what am I going to do? I've got this is heading to infinity, this and this is heading to infinity. When I actually apply this to infinity, I get an indeterminate form, which means I need to use L'Hopital's rule in order to evaluate that. So L'Hopital's rule says I'm going to take the limit as n goes to infinity. I'm going to take the derivative of the top, which is my exponent, times my base, my exponent minus 1, all over the derivative of the bottom. This is the derivative of the top and the derivative of the bottom. These are going to cancel. This, n to the 1 over n minus 1, means I'm looking at the limit as n goes to infinity of n to the 1 over n all over n. This is the n to the minus 1, right? I bring the n down into the denominator. Now I'm still left with something like an indeterminate form, but if I do L'Hopital's again, I'm just going to be basically repeating itself over and over, because I've got this 1 over n to the 1 over n in my exponent here. So I'm going to do a little trick in order to get this out of the position. So I'm going to basically just take a look at this bit right here. Okay, so I'm going to evaluate this bit first, okay, and see what happens. Okay, well the first thing that I want to be able to do is I'm going to say if I go e to the natural log of n to the 1 over n. Now what happens is I get e to the 1 over n natural log of n, right? E to the 1 over n natural log of n, okay, is basically like I'm essentially saying e to the natural log of something is just basically like not doing anything at all, because these two are inverses of each other. But here, if I'm working with that, I can say the limit as n goes to infinity of e to the 1 over n natural log of n is the same thing as saying e to the limit, because this is where my n is happening, 1 over n natural log of n. Okay, so what happens is this bit right here, okay, it looks like I can do L'Hopital's again when I do that, okay, and what happens is that this here goes to 0, okay, but I can do that by evaluating by L'Hopital's. We also know that n is going to reach infinity before the natural log of n reaches infinity, but L'Hopital's will actually tell us that for sure. So we're dealing with e to the 0. So this bit here, which is equal to 1, this bit here is equal to 1. So really, what I'm looking at is the limit as n goes to infinity of 1 over n, right, which is equal to 0, and 0 is less than 1. Since 0 is less than 1, I can then conclude that this thing is going to converge. And it converges by the root test. There was a trick in there, and the trick was basically taking the e to the natural log of that function there. Okay, so that was how I can evaluate this, and then taking the limit of it all.